Delaware Tech, Chemistry 100, Chemistry 110, Unit 4 continued, Intermolecular forces. Intermolecular forces, as the name would suggest, are forces between molecules. That's what inter means, between. Intra means within. So intramolecular bonds would be bonds within a molecule, like the covalent bonds and ionic bonds we've already talked about. These are very different. These are bonds between individual molecules among covalent compounds. So these are forces between them, and we call them intermolecular forces. So these are forces that make solids and liquids possible. And they're also known as van der Waals forces, named after Johannes Diederik van der Waals, a Dutch physicist who first described these interactions between molecules. So they come in two general varieties. There are actually many classifications for van der Waals forces or IMF forces, but we're going to group them into two general categories. The ones that involve dipoles that we've already talked about. So these are molecules that have permanent dipoles. That is, they are molecules where one side is slightly positively charged and one side is slightly negatively charged because they are polar molecules. And those polar molecules can take advantage of what are called dipole-dipole interactions, or simply dipole interactions. You have to have polar molecules only because you need permanent dipoles that are always there. Water, for instance, ammonia, NH3, these are permanent dipoles because they're always polarized. There's always a part of them that's partially positive and always a part that's partially negative. And the interactions between these will depend on how big the molecules are and how they're oriented. You want the positive part of one molecule being near the negative part of the other so they attract one another. The other type of van der Waals force, or intermolecular force, IMF, are called dispersion forces. Dispersion forces are also known as London dispersion forces or hydrophobic forces. These were named after another physicist by the name of Fritz London, who oddly enough was German, though the name might suggest he was from England. He was actually German. And he described these forces. And these are forces that a lot of people are called van der Waals forces by themselves. This isn't quite correct, but it's a very common use of the word. So if you hear somebody say van der Waals forces, most often they're just talking about dispersion forces, especially among biologists and biochemists. So these are molecules that involve temporary dipoles, what we call spontaneous dipoles that happen by chance. And they can happen even in very nonpolar molecules. In fact, both of these interactions can happen in both of these interactions can happen in polar molecules, but nonpolar molecules can only take advantage of the London dispersion forces. Nonpolar molecules can never use the dipole-dipole interactions. So these interactions involve temporary dipoles, and I'll explain what that means in a slide or so, but they depend on the size of the molecule. The bigger the molecule, the more electrons are in the molecule, and therefore the more electrons that can be shifted to one side of the molecule than the other, and therefore you'll have more of a temporary dipole appearing and greater dispersion forces, or greater London forces, or greater London dispersion forces. There are many names for this force. So, dipole-dipole interactions. You need molecules that have a dipole all the time, a polar molecule. So if you have two polar molecules, shown here as HF, hydrogen fluoride. Hydrogen fluoride gas will attract another hydrogen fluoride, especially if you put this in water, it becomes hydrofluoric acid. And the HF will attract another HF. The F is partially negative, the H is partially positive, and the F from one molecule will attract the H from another. There will always be these attractions. These attractions are much, much weaker than covalent bonds or ionic bonds, but there's so many of them, they add up and become very important. So you have these things lined up. There are only partial charges on there, and they're much, much weaker than ionic and covalent bonds, but there's so many of them. Remember, each HF is surrounded by other HFs, and this can happen in all directions around it. And these bonds, being weaker, can break and reform and break and reform constantly, but it will keep them together in a certain to a certain degree. And this is especially important in liquids. Dipole-dipole interactions, these permanent dipole to permanent dipole interactions, are a bit stronger than dispersion forces. Dispersion forces are dipole interactions that are between non-polar molecules that only for a blink of an eye form a dipole accidentally. And I'll show you that later. So they're a bit stronger. So dipole are stronger than dispersion. That's the take-home message. So here's an example of a XY, a made-up molecule that has a dipole. Y is a little more electronegative than X, so it's got a dipole. And there's this attraction between the partial, Y is a little more electropositive, so it's attracted to the more electronegative X of another molecule, and you end up with this dipole-dipole interaction. So examples would be interactions between bromine monochloride, right here. Bromine monochloride with bromine monochloride. One side is partially positive, one is partially negative. The opposites attract. Here's another one between phosphorus trifluoride. The phosphorus is less electronegative. The fluorines are very electronegative. So the fluorines will have a small attraction towards the phosphorus of another molecule, and you get these interactions. And by the way, if you mix these molecules up, they can all interact with one another as well, with the positive end of one and the negative end of another. Hydrogen bonds are a special type of dipole-dipole interaction. They are dipole-dipole interactions, but they are the strongest of the dipole-dipole interactions. And you can tell a hydrogen bond because the atom that's in the middle of the interaction is a hydrogen. You have a hydrogen that's attached to either a nitrogen, an oxygen, or a fluorine, possibly a chlorine too, but those three are the ones that have been definitely shown to be true. And then that can interact with another nitrogen, oxygen, or fluorine on another molecule, and you have this attraction. So it's a dipole-dipole, but it involves a hydrogen. This will not work if it's a carbon attached to a hydrogen, because carbon-hydrogen bonds are very nonpolar. There's only a tiny difference between those two, so there's no polarity and they won't form hydrogen bonds. Just nitrogens, oxygens, fluorines, maybe chlorines. So here's water, the most famous example of a hydrogen bond. The hydrogen of one water, which is electropositive, will attract the oxygen of another water, electronegative side, and you'll get these attractions. These attractions are so important because they're so prevalent in water. There's so many. I've only shown you one interaction between two waters, but imagine every water's oxygen is linked to multiple hydrogens from other molecules, and every hydrogen is linked to multiple oxygens of other waters. And you end up with this very close lattice, and this is why water exists in liquid form at room temperature. If these bonds weren't there, water's boiling point currently is 100 degrees centigrade. In other words, you have to warm it up to 100 degrees to break all the hydrogen bonds and release the water molecules as individual gas molecules. But if these hydrogen bonds didn't exist, water's boiling point would be almost 200 degrees lower. In other words, water would always be a gas, even at 100 degrees below zero. It would still be a gas. So these hydrogen bonds are very important for water to be a liquid, and therefore are extremely important for life to even exist on Earth. Here's ammonia, NH3. The H is more electropositive, the N is more electronegative, interactions. And the fact is, if I put all three of these things in water, they would all attract one another from their positive ends to their negative ends in hydrogen bonds. And you would get hydrogen bond after hydrogen bond, they break easily, they reform easily, and so the liquid will move around. That's why it is liquid, because they're breaking and they're moving, breaking and reforming constantly. If they stopped breaking, if they just held together, well, then that would be a solid form, and that's what happens in ice. Ice, the hydrogen bonds in ice are kind of linked together, and they end up forming the six-sided pattern with the waters, and that's why we have ice crystals that are frequently shaped like six-sided figures. That's why snowflakes have six sides. So dipole-dipole interactions, you can imagine part of the molecule is partially positive, part of it's partially negative. They attract one another, and you can have all of these things linking to each other to opposite charges of other molecules, and they could break apart and find different ones. They can move and find different partners, and that's what makes a liquid possible. Let's talk about dispersion forces or London forces. These are forces that can only occur these are forces that can occur with every kind of molecule, but nonpolar molecules can only use these forces. Nonpolar molecules can't take advantage of dipole-dipole, and they certainly can't take advantage of hydrogen bonds. So London forces can be used by every molecule, every covalent molecule, but they're more important in polar molecules because that's all they've got. So they depend on how big they are, how many electrons they have, and they are the weakest of all the forces holding molecules together. All molecules can use dispersion forces. More electrons, the stronger the force. So why? Well, let's talk about what a dispersion force actually is. Here are two ovals. We'll make believe the two ovals represent two whole molecules. And these molecules have atoms and they have bonds, but we're not going to worry about that. Just think of it as a collection of electrons that are moving around. And we have two different molecules. They're both nonpolar. They don't have sides of them that have more electrons than the other, but the electrons do move randomly. And because they move randomly, every once in a while, one molecule may have more of its electrons on one side of the molecule than the other. So this is referred to as a instantaneous dipole or spontaneous dipole. You can think of it as a randomly formed dipole that just happens periodically with nonpolar and polar molecules. And once you have a dipole formed in one, and if it's near another molecule, well, remember, electrons are negatively charged. Negative charges of the first molecule will repel the negative charges of the second molecule, and so they'll move to the other side of the molecule for just a blink of an eye. This is far, far less than a second. In fact, it's far, far less than a billionth of a second. It's very, very fast, but they add up and they become important. So if you have the second dipole form, because it was induced by the other dipole, we call the second dipole an induced dipole. And I'm not going to expect you to know the name spontaneous and induced. You should just know that a dispersion interaction can happen with all molecules, but it's more important with nonpolars because that's the only thing they can use, and bigger nonpolars have better dispersion than smaller nonpolars. So we now have this temporary pair of dipoles. Well, like any other dipole, they will attract each other. The partial negative side of the left one will attract the partial positive side of the right one, and you get this blink of an eye attraction between these two temporary dipoles. So it's much, much weaker than the dipole-dipole interaction of permanent polar molecules, but it still is effective, and it's very important when you get bigger and bigger molecules. So it's very weak, but they do add up. So bigger molecules have better London dispersion forces. For instance, among the halogens, we have chlorine and fluorine. Fluorine is at the top of the halogens, chlorine is next. These are very small molecules, and they're not polar because they're completely symmetrical, F to F, Cl to Cl, and because they're symmetrical, they're not polar, so the only thing they can use is London forces. Well, the problem is they're too small for London forces to be important. They don't have that many electrons, and therefore they're not held together by London forces, and they're gases at room temperature. Bromine is a bit bigger, going down the periodic table, so it gets to be a liquid at room temperature. The forces are strong enough to hold it together to be a liquid. Iodine is even bigger than bromine, and two iodines linked together, they will attract other I2 molecules with such strong London dispersion forces that iodine molecules are found as a solid crystal. In fact, you can buy crystals of iodine. They're a kind of a dark purple gray crystal. They used to sell them in drugstores. I don't think they do anymore, but they're solid at room temperature. They're big enough to be solid. And the same thing happens with hydrocarbons. Hydrocarbons are molecules only made of hydrogen and carbon, hence the name hydrocarbon. So CH4, methane, C2H6, that's ethane, These are the two gases that make up natural gas. Methane is the more prominent one. The third one, C3H8, I'm sure you've all heard of, that's propane. And C4H10, that's butane, as in a butane lighter. So all of these are small enough molecules that they're gases at room temperature. They're not that big, they don't have many electrons, therefore their London forces are not very strong, and none of these are very polar because they're only made of hydrogens and carbons, and the difference in electronegativity between hydrogen and carbon is very, very small, about 0.3. And as a result, the difference being so small, they're pretty non-polar molecules, so the only thing they can use is London forces. The problem is they're too small to even make use of that. If you get bigger, C5 up to C16 hydrocarbons, now they're liquids. One of those would be C8 H18, that's octane, that's your gasoline, and you know that that's a liquid at room temperature. If you go bigger than 17 carbons, now they're so large that the London forces are really important and they start becoming solids at room temperature. So just to review, you don't have to know these numbers by any means. This is just to show you a comparison of bond strength. So we have the intramolecular bonds, the true bonds, ionic bonds and covalent bonds. I've also included metallic bonds in case you're studying those as well. I've also included individual ionic bonds. So it's one bond between, say, a sodium ion and a fluoride ion or a chloride ion in salt, as opposed to a lattice where you have, if you look at the whole crystal, every sodium ion is surrounded by chloride ions, and every chloride ion is surrounded by sodium ions. So the energy is much, much higher if you really look at the whole crystal. So you can see all these numbers are relatively large numbers in comparison to the intermolecular force numbers. Hydrogen bonds, the best of all the IMFs, has an energy, and we're not going to worry about the energy units here. These are kilojoules per mole. We haven't talked about what a mole is, but just think of it as a certain amount. So it's amount of energy per a certain amount of molecules or formula units. So 4 to 50 for hydrogen bonds, 2 to 8 for the other kinds of dipole-dipole. Remember, hydrogen bonds are the best type of dipole-dipole. And then London dispersions can be anywhere from 0 to 4. They're very tiny. Some people have found something possibly up to 63, but that's not really well established. So in general, London's dispersion forces are the weakest of all the forces. Dipoles are stronger, and the best dipole-dipole is a hydrogen bond. But all of these are very common, so that there are many, many of each of these small numbers. They add up, and they start becoming important. But they are all, as an individual interaction, much, much weaker than the true bonds within molecules, the intramolecular bonds, like ionic bonds and covalent bonds, that are in the 100 to 500 kilojoules per mole range. So, to review, dispersion forces, these are the weakest of the IMFs. They are between temporary dipoles. They're useful for non-polar molecules that can't use a dipole-dipole interaction, but all molecules can take advantage of them. Dipole-dipoles can only be used between permanent dipoles, that is, between polar molecules. They have to always be polar. One side has to be more electronegative than the other. They can't be symmetrical. And therefore, these interactions are going to be stronger because they're always there, they're always available, and the energy is a little bit higher than the dispersion. And the hydrogen bonds are the best type of dipole-dipole. They're a special type when you have hydrogen bound to a fluorine, an oxygen, or a nitrogen, maybe a chlorine. I'm not going to test you on chlorines, but you should be able to recognize the others, especially in water. Water is the best known example. And there, the hydrogen is the center atom in this interaction between two other electronegative atoms, bridged by an electropositive hydrogen. And they're the strongest of the IMFs.